right?
Uh, Majority are mathematician here.
Oh, they are mathematicians. Oh,
Yeah,
cool.
yeah. So
Okay,
because we
so
are mathematical lab, so but we study biological system using mathematics.
okay, so
Yes.
are you guys familiar with the partial differential equations and
Yes.
physical simulation? Okay, so solving the numerically, that's
But
pretty
we are not expert about numerical method, but we know the PDE. Yes.
okay, cool. A lot of physical systems, as you know, described by partial differential equations, right? Describing Navier-Stokes for the fluid simulations or the Maxwell's equations for electromagnetic systems, or the some elasticity or some plastic elasticity. All those the physical simulations can be described by some sort of governing equation, some sort of partial differential equation. I mean, the small scale, like the Schrödinger equation, is also the partial differential equation. But those a lot of times those partial differential equation has to be solved numerically because of the complex geometry and there is no analytical solutions. You cannot solve it with pen and paper, right? So we're relying on the computers and well, thanks to our pioneer, like starting from 1950, 40s, uh, the advanced computer system has been developed, and since then, you know, according to the Moore's law, the computing power has been advanced like the doubled and and along with those computing power development you know people like you the applied mathematicians pure mathematicians came up with a functional analysis and came up with this numerical schemes of the solving partial differential equations. Thanks to them, right, we are now can solve very complex physical systems um, and can get the solutions any space and time very accurately with a high precision. So that's great. With those tools, we can do a lot of stuff, even the biology, right? We can try to model the physical model, try to mimic the some biological systems, which we cannot easily do the experiment with, right? However, the problem is that as the model and the problem become, the domain becomes complex, the domain's complex increases, um, the numerically solving that is challenging. So, for example, here I brought many different physical simulations, which is built in our lab, and as you can see, even using the high performance computing at our lab, like it's pretty big. Even with those big machines,
Mm-hmm.
just solving one fold simulation takes like 1 week
Mm-hmm.
with 108 cores, or using the 1024 cores, and it takes a 1 week. Very long time. So that's a problem because in decision making problems like uncertainty quantifications or design optimization, you would like to solve these fold simulations many, many times as you explore your parameter space. So that's the problem. But thanks to, recent advances in machine learning and artificial intelligence, now we can use data to accelerate these physical simulations. And one way of accelerating those physical simulation um, is the LaSDI, which I would like to introduce you to you
Mm-hmm.
today, which is so-called the latent space dynamics identification. As I said before, it is data-driven approach. So of course you have to generate the data. A lot of times we generate those data using physical simulations, and those physical simulations generate high dimensional the data. And you know, it's hard to fit those high dimensional data into some sort of model. So what LaSDI does is it applies the some sort of compression technique to reduce the size of the data into the very small scale. And once the data size becomes small
Mm-hmm.
scale, it's now all of a sudden easy for us to fit that into some sort of model.
Mm-hmm.
And our group, we try to fit those reduced data into some sort of differential equation form.
Mm-hmm.
We chose differential equation because our mathematicians, applied mathematicians, they understand much better on the differential equation than the neural network, which is considered to be black box these days. So we chose the differential equations to increase the interpretability and identify those differential equations. And also we try to parameterize it because once we train this LaSDI model, we would like to predict the new solutions, right? By changing the boundary conditions or initial conditions, etc., etc. So those boundary condition, initial conditions, or material properties parameterize and directly change these differential equations.
Mm-hmm.
That's okay. Even though we parameterize these differential equations, getting the solution of the parameterized equation is still computationally cheap because
Mm-hmm.
this differential equation is the model for the reduced space, not the full space.
So
So
here U hat is a reduced variable for the latent space system.
U hat is, yes, exactly. And the size of the U is usually million or billions or even
Mm-hmm.
bigger. But the U hat, the typically size is 10 or 20
Oh,
or
I see.
100.
Okay.
Yes. So this number of the ordinary differential equations or partial differential equations is 10 or 20 or 100. So you're solving that differential equations numerically still is very cheap and computationally efficient. So you do that and get the solutions in the reduced space, right? So that is the solution of the U hat, right? And then during the compression steps, if you use the autoencoder, then there's a encoder and decoder, so you can use the decoder to bring the reduced solution back to the full space. Or if you use the POD, like the SVD type, singular value decomposition type linear compression method, then you can do the transpose to the compression and then just do just normal multiplications to reconstruct the solutions. But the bottom line is that once you get the reduced system solutions, you can project back to the full space and recover the whole space-time history for your physical system. So it's sounds pretty simple, right? The
Mm-hmm.
LaSDI, latent space dynamics identification, but it does provide very rich framework. You can come up with many different types of algorithm, even just following this framework. And as a matter of fact, we have recently published, I think, 5 or 6 different versions of the LaSDI
Mm-hmm.
by adopting different identification techniques,
Mm-hmm.
different compression techniques, and different data generation techniques, or even combining, the compression and identification steps, like, make it simultaneously. Yeah, so it looks simple, but it does give you very rich framework
Mm-hmm.
where you can come up with um, um, very advanced the algorithm. Well, why is that important philosophically? Because in my view, there will not be a one data-driven algorithm which can solve every types
Mm-hmm.
of
Mm-hmm.
the problem. So I strongly believe that you must have a some tailored algorithm which is some specific to certain applications depending on the characteristics of the dynamics, etc. So the providing this rich framework is very important. So just to give you an example, data generations, you can apply a priori sampling approach like the uniform sampling or Latin hypercube sampling. Very simple, but the generating data, if the generating data is very computationally
Mm.
expensive, then you cannot afford those uniform sampling or Latent hypercube sampling because they will are likely to require you to generate many data. So in that cases, you probably want to take the active one framework where you smartly sample your parameter space by using some uncertainty the information or some physics information. Compression, two obvious options are linear compression or nonlinear compression. If your dynamics is very compressible in linear sense, then the linear compression, such as singular value decomposition, is suitable. So you just go with it. Just use that. You don't have to go through the nonlinear compression because nonlinear compression is very computationally expensive and right and sometimes the compression rate is not that good. However, if your dynamics are not linearly compressible, for example, Kolmogorov width is decaying very slowly, like the advection dominated problems, or each snapshots are very linearly independent, then you have to apply the nonlinear compression, such as auto encoder.
So, Dr. Chen, so
Yeah.
when you perform the singular value decomposition, then what is the where the matrix comes from in this system? So matrix
Yeah.
so what
So
kind of number? Yeah.
yeah. So for example, let's say you have this plasma related simulation, 1D, 1B philosophy equation. This is the solution, like the dynamic solutions.
Yeah.
And you generate using the simulation.
Uh-huh.
And what we can do is, it has a time dimension and the spatial dimension, right?
Yes, yes.
And you can put all the spatial dimension into, you can vectorize all the spatial dimensions. And for first column, you put the first time step solution, and second column, second time step solution, and so on. And that will give you a snapshot matrix.
Okay.
So that's the data. So SVD is a solution. If you just simply apply the SVD singular value decomposition on those snapshot matrix, it's going to give you a optimal solutions of so-called proposed order decompositions.
Okay.
Where your snapshot matrix minus whatever the basis you're looking for times the generalized coordinate, it minimizes those difference in Frobenius norm. So that's where the matrix comes from, and yeah, it does give you some optimal property. However, you can easily see that if your solutions are linearly independent, right? Just what you get from the advection dominated problems, like that many hyperbolic. When you solve the hyperbolic problems, you get very linearly independent the snapshot matrix, and it's not compressible, right? If you do the linear compression. So if that is the case, then you better off using the nonlinear compression.
I see.
So the point of this compression is you gotta know about your data, and if you know, then you can choose either linear or nonlinear compression. Okay. So the next step is identification, which I'm going to focus on if I have enough time. I will show three different types of identification: physics guided and equation discovery and fixed form. Well, I will go into detail in later slides. So let me move on. The next one is the regressions, and once you identify these differential equations, there will be some operators, and what we usually do is we take those operators, specific operators corresponding to training data, and then transform those and make it dependent to your parameter, like the parameter which changes your boundary condition or initial conditions through some sort of regression technique, kriging, the hyper networks, or many other options are available in this frame. So once that is done, then now you have a parameterized differential equations in the reduced space. And as I said, you get the solutions and project back to the full space and yeah, and so on. And okay, let me focus on the physics guided
Yes.
the first identification approach. You may or may not heard of this so-called projection-based reduced pseudo model. It's been a while. So machine learning has been got into the scientific simulation regime because of the popularity of DeepMind beating the Isidore in the the game like the Padu, right? And then it got popularized and everyone and also the protein folding problems, it was really sensational, and now it's affecting everyday life, and even like this scientific computing regimes, the machine learning is affecting in great deals. But even before that, machine learning comes into our community, our field, and really giving us an impact, like 3 or 4 decades, even or earlier than that. These people, very, well-known mathematicians and applied mathematicians have been working on this so-called projection-based reduced model, and that's exactly follow what machine learning people do. Like you generate the data and use those data, and actually do much more sophisticated approach than current machine learning people does. Okay, so let me introduce what they do, and this projection-based reduced model is actually falls into the LaSDI framework I just introduced in previous slides. So the projection-based reduced model, it follows the LaSDI framework. Like the first one is, well, first you have to generate the data, right? And then once you generate the data, it does do the compression. And the same as LaSDI, you can apply either SVD, POD, proposal, or decomposition, or autoencoder. Let's say you got some reduced basis by doing the truncation of the SVD, etc. And let's denote it as a phi here, reduced basis phi. And after that, what projection-based reduced model people do is um, they utilize, maximize the utilizations of the existing governing equations, right? Whether it is Navier-Stokes or and whatever that is. Usually it is described by partial differential equations, and once you discretize in space, you will have a high dimensional ordinary differential equation system. And what this projection-based reduced model people do is plug those reduced basis solution representation, which is denoted as, if it is linear subspace map, the representation, then denoted as some offset F reference, some vector plus this reduced basis times generalized coordinate F hat. So phi is known, F reference is known, and only thing you don't know is F hat, but whose dimension is very small. Like unlike this semi-discretized version of the ODE where the unknown dimension is million or billions, this reduced system is the general coordinate dimension is 10 or 20 or 100 only. So once you get this solution representation, this projection-based reduced model, people plug this solution representation back into the governing equations, and imagine what that happens if you do that. Then it's going to automatically reduce the number of unknowns from billions to 10 or 20 or 100, right? So it tremendously reduced the number of unknowns, but still you have a million or billions degrees equations. So you have to, in order to close the system, you gotta do something, and one way of decreasing the number of the equations is applying some sort of projections. And here, if you use the Galerkin projection, it's nothing more than just multiplying phi transpose both sides, right? Then phi and phi transpose shows up, and because of the usually this phi is also on a matrix, and phi transpose phi disappears, and only p f hat dt remains, and the right-hand side ended up with this form. And if you look at closely, all the dimension is now reduced dimension. Like the number of equation is reduced in reduced size, and the number of unknowns is also reduced size. So this ended up, giving us a differential equations, system of differential equations for the reduced space. But by the construction, what did we do? How did we derive these differential equations? We derived it by plugging this compact solution representation back into the governing equation. So we did use the physics, and the physics. What I mean by physics is we did use the governing equation that describes the underlying physics. So this way of identifying the differential equation is completely physics driven. So that's what I mean by the physics driven identifications. And once you get this reduced system of ordinary differential equations, you can solve it in reduced space and process back to the full space, and etc. etc. Just following the story I've been telling you so far. Okay, so as I said, this method has been around and developed by great mathematicians like past 5 decades, right? So rich literature and work and exists, and you can find it very easily from many journals, papers. And one of the great benefit of this approach is it's because it is not only using the data but also the underlying governing equations. Extrapolations or generalizability is much better than other purely data-driven machine learning approach. So, for example, here we have generated one type of the physics problem, so-called the Seidel-Blast problems, and for one particular parameter point, we generate those data because it's a dynamic time-dependent problem, so we can collect many snapshots, and using only constructing those snapshot matrix from only one simulations, we construct the projection-based reduced model for that local point, right? And then we try to generalize, those the model for different points which is outside of that local point. And as you can see, for all three different fields, like the position, velocity, and energy, basically we are solving the Navier-Stokes type of hydrodynamics problems. All of them was like close to 1% or less than 1%, for even though we go pretty far away from the training data. So which proves like demonstrating pretty good extrapolation and generalizability. But if you use the black box approach, as soon as you go out, step away away from your training point, which is 0.25 here, it just blows away. Which makes sense because purely data-driven approach has not seen the data outside of the training region, so it doesn't know what to do with it, right? So that's the great benefit of using the incorporating the physics into the data-driven approach. Well, since this projection-based reduced model has been around for many decades, there are many different variants to the standard projection-based reduced model I have just described. I just wanted to introduce some of the variants our team has developed, right? I would like to advertise our stuff. Why should I advertise other people's stuff? Right? So first one we have developed is the space-time realm. So as the name tells you, here not only we introduce the video spaces for the space, but also the temporal domain. So by doing so, you can actually maximize the reductions, right? So if you just apply the spatial reduced spatial basis, then you can just reduce the spatial degrees of freedom from million, billions to, 10, 20, or 100. That's great. But what if you have like also million time steps? How can you decrease that? One way is you also reduce the temporal dimensions by constructing the reduced spaces for the temporal domain. And you combine those spatial bases and temporal bases in some sort of canonical product fashions and build a space-time basis. And you follow the same rules, same procedure. You plug those space-time bases into the governing equations and do the projections and come up with a reduced system of equations. And here, because we reduced the temporal domains, we ended up getting, one like, just one system of equations you have to solve. It's not an ordinary differential equations you get, because the temporal dimension is gone after the reductions. So one solve in the reduced space, right? Whatever that is, it could be linear or nonlinear, but one solve is going to give you both space and time solutions everywhere once you reconstruct to the project back to the full space. So we have done that, and we wanted to challenge ourselves. So we applied this space-time one to, pretty notoriously known to be very high-dimensional problems, Boltzmann transport, the particle transport problems, where it has a, I don't even remember, 40 billion degrees of freedom in space and time, and we were able to reduce that to only 10 space-time reduced dimensions, and we were able to obtain a speed of 2,700 and less than 1% relative error. So, so if you are interested in what we have done there, you can take a look at this paper. Okay. The next variant is the Lagrangian one. A lot of times, your some numerical schemes, you want your underlying mesh, like do you see this grid or mesh is moving with the field. So sometimes you want your numerical schemes of the solving partial differential equation to follow those underlying mesh or the grid, the discretization to follow the field. To preserve, your physical property better. If your underlying numerical scheme is like that, then reducible model guy, they have to also represent the mesh motions as well, not just the field. So by introducing a reduced basis representation for the mesh motions, you can come up with this Lagrangian reducible model. Well, so far, all those reduced model I have, described and demonstrated in terms of linear subspace method. The previous slide, was using the linear subspace method, and the space-time realm and Lagrangian realm was also using the linear subspace method. But as I showed in the beginning of the slides, you could use the neural net type of nonlinear manifold solution representation, right? For example, using autoencoder. And as I said before, that's great for this kind of advection-dominated problems. And, so this so-called nonlinear manifold reduced model is using that nonlinear manifold solution representations. But I didn't go into the detail, but when you have the nonlinear, when you are dealing with the nonlinear problems, simple projection-based reduced model is not going to give you the speed up or great accuracy. You gotta apply, the special technique called the hyper reduction in order to reduce the complexity of the nonlinearity. I mean, reducing the number of unknowns and reducing the number of equations, it's not enough, because your implicit nonlinearity inside of the equations still scales with the full order model, so you have to reduce that complexity as well. So one way of reducing the complexity is applying the hyper reductions, and our group, for the first time, were successfully applied this hyper reduced nonlinear manifold, and practically showed, although it has been shown to the 2D bubbles problem, but it has been shown greatly. All right, so before I move on to the second identification method, I would like to go over one more projection-based Youngsoo model. I'm pretty excited about this approach. I will tell you why pretty soon, but it's so-called the component reduced model, or, what is this? Sorry about this. Oh, you probably don't see that. Only I'm seeing it. Okay. Okay. Oh,
Oh, it was zoom in,
oh,
I think. Yeah.
yeah. Okay. So it's so-called the component ROM, or the data-driven finite element method. I'm pretty excited about this, and I will tell you why soon. So but in order to explain this, I have to assume you guys know something about the finite element method, but probably you guys are not familiar with the finite element method, because you guys are not familiar with the numerical schemes of solving the partial differential equation. So one way of solving the numerically solving the partial differential equation is, you pick, it's so-called the finite element method, and in finite element method you pick some sort of element, right? It's a tetrahedral or triangular elements if it is 2D problems, and it could be quadrilateral. Whatever the element shape is, you pick an element, and then what FEM or what finite element method does is it assigns a polynomial basis on each element. So that will represent the underlying the solutions within that element. And then what FEM or finite element method does is you glue a lot of elements together to form this complex domain, right? So as you can see, it has individual pixels, and individual pixels are like this, the tetrahedral element, right? So you glue them together and form a computational domain, and then you solve underlying partial differential equations with these discretizations, where each element solution is represented by polynomial. But polynomial does not know anything about your problem, right? It's just generic forms, right? So in order to improve the accuracy of this finite element method for complex geometric domain, the complex problems, what people usually do is they decrease the size of this element. It's called the H refinement, or they increase the polynomial order to increase the expressibility of this polynomial, right? Linear polynomial will, the quadratic polynomial should be able to represent more solution space than the linear polynomial, right? The cubic polynomial should be able to represent more solutions space than the quadratic or the linear. So the same concept. You increase the polynomial order in order to increase the accuracy. So, but the problem there is, as you increase the polynomial base, polynomial order, or as you decrease the element size and introduce many more element in your computational domain, in either cases, you will increase the size of the problem. So that's why, in previous slides, when you discretize in space, usually in full space, you're dealing with million or billion degrees of freedom, the unknowns. So we don't like that. And that happens because this polynomial does not know anything about the problem. So how can we fix it? We can actually replace this polynomial basis with a data-driven basis. So what I mean by data-driven basis is the data-driven basis I have already introduced to you when I explained in the projection-based reduced model, like those linear source-based solution representations or nonlinear manifold solution representations, which you derive from the data. But in this data-driven finite element method, the idea is that you build this data-driven basis from the data that is generated on this smaller scale element size, right? So because it's a smaller scale, generating the data on those smaller scale, it shouldn't be expensive, computationally expensive. And as a matter of fact, you can generate tons of those because it's so cheap to computationally cheap, efficient to generate those data in the smaller scale. And using those data, you can build a data-driven basis for each element, right? And then you follow the traditional finite element method approach, like you assemble them together, glue them together to form this complex geometry and solve the partial differential equation using those bases. Why is it? It's a very pretty innovative and pretty good idea because this data-driven basis knows about your problem through what? Through data. And because of that, the quality of the basis has increased tremendously. And because of that, you can use the much bigger element size than the traditional finite element method. And because of that, the problem size becomes not much bigger, not much. It doesn't become large scale, just like the traditional finite element method. So you can solve even larger problems which you couldn't solve with the traditional finite element method. So a lot of benefits. Let me just skip those things. And let me just show you what we have done with this data-driven finite element method or component reduced model. So we were able to solve this lattice structure design problems where lattice comes with very different the component the repeated components, right? And it's so natural that these repeated components can be used as the element in the data-driven finite element method, right? And you follow those the data-driven finite element method procedure, which I just described in previous slide, and then form a data-driven basis for each component and assemble them together and form a lattice structure and solve the underlying governing equations for this structural problems. So this is actually linear elasticity, the governing equations we have solved. Because this data-driven approach was giving us a pretty efficient way of formulating the problem, we were able to obtain a speed of 1,000. And because it was so fast, we were actually was able to solve a topology optimization problem where we start with a lattice structure with L shape like that, completely filled with this component. But in topology optimization, we minimize those weights by removing unnecessary components automatically through the optimization process, and then without breaking solutions, and the topology optimization was able to give us a optimal shape optimal shape was looking like that. Pretty cool. And this data-driven finite element method was also is extendable to the porous media flow, Navier-Stokes porous media flow problems, which is nonlinear problem, unlike this linear elasticity problems. And using the hyperreduction techniques, you can also apply this, come up with this data-driven basis on each component and assemble them together and solve a much larger scale problem and obtain a scale-up effect of 256 and also with a pretty good accuracy, like less than 1% together. And the same technique can be applied and to the time-dependent problem, right? So this is the field are moving. The idea is the same. You trained your data-driven basis in the smaller scale, and then once the data-driven basis is achieved, obtained, you assemble those small-scale elements together and enable this much larger scale the problems and obtain pretty good speed up, right? Close to the 700, and then with relative error less than 1%. Okay. Enough for the physics constraint and physics guided the identification. The second the identification a method I would like to introduce is the equation discovery-based identification. So the projection-based reduced model or the physics-guided data-driven approach, it was assuming, you know the governing equations. But what if you don't know the governing equations? You only know the data. And a lot of biological system is like that, right? I mean, you don't exactly know the governing equations. But you do have the data, some measurement data or some scan data, etc., and etc., some experimental data, etc., etc. So in those cases, right, since you do not know the governing equations, but you only have the data, and probably you have a high dimensional data, you still apply the compression technique, right? Okay, so you still apply the compression techniques, but you do not know what would be the governing equations for this space, right? But you do have the data because you just compress the data into the reduced space. So in that case, you can apply equation discovery algorithm, so-called the SINDy, like sparse identification of nonlinear dynamics, which is popularized by University of Washington people, Stephen Brunton and Proctor and Nathan Kutz. So the SINDy, how it works is as a user, you can define what kind of the nonlinear function library you would like to use on the right-hand side, which is represented by this phi. And it could be polynomial representations, the trigonometric representation, or exponential representations. You provide those library, and then now you try to fit those data into this ordinary differential equations with the right-hand side, which is determined, provided by you as a user. Then you solve a regression technique. You apply the regression technique to determine a coefficient of this individual, the right-hand side terms you have provided as a library. So and SINDy, they impose the constraint on this coefficient to be as sparse as possible, so that they can get some sort of parsimonious representations of this ordinary differential equations, to removing unnecessary nonlinear terms you have initially provided and come up with a simplest form in the ordinary differential as an ordinary differential equations. So it's beautifully worked very, very nicely, as long as your data is noise-free. But a lot of times, if your data is coming from experiments or measurement data or image data, a lot of times it comes with a noise. And if it comes with a noise, because this SINDy is using the strong form, and if you had is the reduced data from the original data, if the original data is noisy after the compression, this reduced data will be also noisy. And in order to compute the DUDT, you probably have to do some finite difference to approximate that. But doing the finite difference on the noise data is going to completely corrupt the derivative informations, with this strong form. So it's not robust for the noise data because of this strong form. And as a matter of fact, we experiment and added some white noise everywhere, and then tried this strong form in LaSDI framework, and as we expected, we got like 40% relative error. I mean, in eyeball norms, this looks different from this, right? I mean, make total sense. So in order to address that issue, what you can do is you transform those strong form to the weak form. So by introducing some smooth test functions, whose derivative everything about it, right? I mean, you have a total control of what kind of test function you can apply. And choose those test functions and multiply that test functions on left and right hand side of the strong form, and then put the integral in time, because this is the time domain, time dependent problems. And then you do the integration by parts on this integral. using the divergence theorem, and you apply by doing so, this derivative of on the data, which is noise data, will go to the test function whose derivative you know everything about, right? So now at the end you had here no time derivative on that, and you get d theta over dt here, which is completely great, and it's perfect, right? So that's it's definitely helping if your data is noisy. In addition to that, because we took the integral in front of it, so integral is pretty much like doing the summing or averaging effect. So it's naturally smoothing those noise data as well. So it has like the double effect, which is improving the noise data by just simply the transforming from the strong form to the weak form. So that's that's what we did, and we call it weak form LaSDI and WLaSDI in short, and we applied that to the same noise data, and instead of the 40% relative error, now we get the 5.6% relative error. Pretty cool, right?
Mm-hmm.
Okay, so this and the equation discovery based LaSDI is purely data driven. It does not use it does not even assume you know the governing equations. So it's pretty easy to apply to any type of the problems, and we were able to apply that to many different types of physical problems, and one of them is energetic material pore collapse simulations, where you can see the shock is moving from left to the right, and there was a pore, and as the shock hits the pore, and the pore is collapsed, and as the pore collapses, the so-called hot spot generated, where the temperature is increasing crazily, and those mechanism is pretty important to understand to to design the energetic materials, and this microstructure like of the temperature field after the pore collapse, this like the spider shape web kind of the shape, the capturing those as accurate as possible was very important, and we were able to do so using this the LaSDI framework, which is purely data driven, and also we were able to apply that to the whole run the problem. I don't know, like the 1 year ago or 2 year ago, our Lawrence Livermore National Lab, for the first time in human history, we were able to enable the fusion ignitions, generating more energy than the input energy. I don't know, you guys haven't heard of that use before or not. I mean, I have seen them use the KBS or the NBC. Those were broadcasting those experiments. But this whole run problem is related to that, like so-called ICF, like the inertial confinement fusion. And through the inertial confinement fusion, they were able to obtain more energy than the input energy through the fusion process. And this, the whole run problem, it's important to, so here you are providing the energy, the radiation energy from top and bottom, like the uniformly. And there's a capsule in the center, and it is important to obtain a uniform as uniform as possible, like the temperature on the surface to be as uniform as possible. So it's kind of control problem we are trying to solve, but to solve the control problem, you have to accelerate the underlying physical simulations. So for underlying physical simulation is the so-called TRT problem, thermal radiative transfer problem, and which is also notoriously known to be very high dimensional and very computationally expensive. So we use the LaSDI framework to accelerate these physical simulations, and were able to obtain the accuracy in whole domain, like less than 3% relative error everywhere. And of course, we were able to obtain like the speed up, I don't know, like thousands of the speed up instead of like hours and hours of the the full auto model simulations. We were able to finish that like 8 seconds. using those LaSDI data-driven LaSDI framework. Okay, let me move on to the third identification the method, and the first fixed form, which is called the fixed form identifications. The first one I was about to explain you was so-called the DMD, which is a pretty famous one, the dynamic mode decompositions, which is using the linear ordinary differential equation as a fixed form. But since it is pretty well known, let me just skip to the last topic, which also another topic I'm pretty excited about, so-called the thermodynamics-based latent-based dynamics identification method. Okay, so instead, I mean, unlike the DMD, where it uses the linear ODE in the latent space dynamics identification form as a fixed form, this thermodynamics, the LaSDI, it uses the partial differential equation form, but which is popularly used in the thermodynamics community. So for the compression, for example, compression, we are going to stick with the autoencoder. You're gonna see why we stick with the autoencoder. But the latent space, we are going to use a fixed form, so-called generic equations. And the generic equation, it stands for general equation for non-equilibrium reversal irreversible coupling formulation. Whatever that is, I'm not a physicist, but it has this form of the partial differential equations where the z is your latent space variable, and z dot is the time-dependent time derivative, like the dc/dt, right? And then L is the operator you have to identify. Well, there are four operator, two operator and two variables in these generic equations. L is the matrix, like the operator, which is the Poisson matrix. M is the friction matrix, another operator. E is the first variable, energy, and S is your entropy variable. And these operator and variables has to satisfy these four conditions, where L needs to be the skew symmetric, M needs to be symmetric positive definite, and E, the derivative of E should be resides in the null space of M, and the S, the derivative of S has to reside in the null space of L. So if these four conditions is satisfied, then whatever the solutions of these generic equations will satisfy the first and second law of thermodynamics. The first law being the law of conservation of energy, the second one being entropy always has to increase, right? Well, we have, I mean, this generic equation has been, around since 1997 by these two guys, but it was not data-driven approach. So in order to make the data-driven approach, we have, generalized that. So each operator and variables is represented by the neural network, right? And once it is, when we train the neural network, we enforce those four conditions, right? You have to satisfy, right? Otherwise, it's not a generic equations. And you train the neural network and with those constraints, and once the training is done, the form, like the representation of each operator and variables, will be determined by the neural network, and these four conditions are automatically satisfied. So that's how we form the LaSDI, which is the thermodynamics-based latent space dynamics identifications. And let's see what happened. So very simple problem. We have applied that to the 1D implicit Burger's equations, and as you probably very familiar with, the Burger's equations, it starts with some initial conditions, and as you go, the time passes by, it's some sort of the shock is formed. And we have applied the LaSDI to that problems and observed the entropy in the latent space, and we noticed that entropy was increasing. I mean, as I said, right? That's what genetic equation does, right? The first and second law of thermodynamics has to satisfy. But if you observe the rate of change of the entropy in the latent space, we see some different behavior in the latent space depending on where you are in time. In the beginning, it was not that the rate of the increase was not that big, but at some point it was increasing, increasing, and increasing. And we noticed that that actually corresponds to some dynamics in the whole space. If you look at the Berger's equations, you start with the Gaussian-looking initial condition depicted by this blue line. And as the time goes by and it's skewed to the right and right, and at some point it's going to form a sharp, right? And we noticed that this increase in the entropy of the rate of change in the latent space was correlated with what's happening in the full space. So is it coincidence? So just to double check, we now applied this T-LaSDI to the heat equations. And then if our observation is correct, then the reverse phenomena should happen, right? Because the diffusion problems, starting from some disturbance, non-zero disturbance, and then through the diffusion process, everything becomes uniform, right? So, rate of the increase, rate of change in the entropy in the latent space has to start from some high value in the beginning, because it was, it starts with a non-uniform initial conditions. But as the diffusion process goes on, those rate of the change in the entropy in the latent space has to decrease, and as we expected, it was doing, and it was correlated to this full order model dynamics. Okay, so why am I so excited about this? It sounds very simple, and it looks obvious, but this is just giving you a one-way. It's just demonstrating what this LaSDI framework can do. So if you put some different physics into latent space, and you combine that, integrate that training with a autoencoder, right? So you simultaneously train the autoencoder and those the system identification for the latent space, and you intentionally put some known physics into the latent space. Then what this autoencoder does is whatever that the physics in the full space, it will transform that to another physics in the latent space. So here in these examples, we happen to use the thermodynamics equations in the latent space, but it doesn't have to be the thermodynamics. You can put some the Maxwell's equations, you can put Navier-Stokes equations into the latent space, and you can use the data in the full space from some other physics. And through this framework, what it does is that it's going to transform one physics through the autoencoder to the another physics, and the autoencoder is going to figure out the correlation between those two. And why is it so exciting? It's because the latent space is so efficient to solve, as I said before, and because it's representing some physics, and it will have some physical property to observe, right? Depending on what physics you are dealing with. I mean, for thermodynamics, it was energy and entropy, but for other physics, it could be some other quantity, right? And those quantity, this autoencoder is going to give you some correlation between those quantity with whatever happening in the full physics. And once that correlation is identified, you do not have to go back to the full space to analyze things. You only need to remain in the reduced space, which is pretty efficient space, and do the analysis pretty quickly and pretty thoroughly and pretty interpretable way. And it's in my view, in my perspective, this T-LaSDI is demonstrating, like, opening the window of those new way of transforming the one physics to another physics. So, okay, with that, I would like to conclude my talk. And a lot of the materials I have presented is actually can be regenerated by any people in the world because we enable our we open sourced our code, make it available to everyone. And we made a lot of resources available to you, like YouTube tutorials about some of the stuff I have presented today is available in very short, like 5 minutes, 10 minutes length of the tutorial, and also the open source code repository is available in GitHub, and the Librem.net webpage is also available, introducing many other stuff which I haven't covered today. And also, compiling the code is pretty, it could be pretty hassle. So we already pre-compiled everything in the cloud, AWS cloud. So if you guys have access to the AWS, then you could grab the compiled version and generate the data and play with it pretty easily. And with this beautiful, the pictures of beautiful collaborators, let me just end the talk. I guess I went too far. I went too long. So sorry about that.
Thanks so much. So, because we have only a couple minutes, maybe we can have a one or two quick questions. So, is there anyone who want to ask a question?
Can I ask something about?
Sure, Dr. Joe.
Uh,
Please
First of
introduce
all,
yourself.
네, nice to meet you. I'm Hyuntae and working at Korea University Sejong campus. I'm also interested in scientific discovery using machine learning or some numerical techniques.
Mhm.
Is it clear?
Thank you.
So,
Thank you. Nice to see
yeah,
you.
I understand that we can convert the strong form to weak form by using the smooth test function due to the data noise issue, right?
Mhm. Mhm.
So in order to realize the weak form in our Python or some numerical programming, so we first describe the definite integration, and second we need to select the suitable test function. Thank you for
Mhm.
the sharing. Uh,
Mhm.
here. So how can we describe, in this case, how can we discretize the definite integration? Is there any popular way? And the second question is how can you select the test function?
Okay, so I would like to introduce another paper, so-called the weak form SINDy. It's not by our group, but the University of the Colorado groups. And we basically follow their routines, like the weak form SINDy, and integrate those weak form SINDy into this LaSDI framework using this compression and simultaneous training, etc. and etc. But what they did as a discretization of the temporal domain is they used the test function, which is piecewise smooth functions like the Gaussian looking the test functions, but they didn't use the Gaussian function. They used like I think the sine or cosine, that some sort of the trigonometric functions they used. But they chose truncate that so that it's only compactly supported, and
Uh,
introduce many different piecewise those cosine or sine functions next to each other.
yeah.
Uh, but it's important that those the piecewise those compactly supported functions are overlap to each other. It's you have to do when you actually apply this Wix in LaSDI in numerical way, you gotta do some hyperparameter tuning as well, just like the neural network. And the overlap, how much you overlap, and how much those test functions you introduce for given time domain, those are some parameters you have to play with. But the rule of thumb, the more the overlap is the stable it behaves numerically. So that's what we have been found. And they go ahead and also, came up with the framework so-called the Wendy, Wendy, And there, they also look into the norm of this test. Okay, so here they simply, original SINDy, they simply apply the test functions here, but it's kind of using the Euclidean norm, like the inner product. But when you define the inner product, you could introduce some the symmetry positive definite matrix induced inner product. And Wendy actually, exploit those inner product as well, and to improve the the behavior of the weak SINDy. So those two papers, I would like to introduce the recommended.
Thank you for.
So they are those papers are written by this David Borch and Dan Messenger, those two folks.
Thank you for the explanation.
Right. Okay. Any other questions? We have 1 minute. Okay. Okay. So then let's thank the speaker. I will upload the video to the YouTube, and then if you have, I think, question, I think you can contact him via email.
Yeah, definitely.
Yes.
Yeah, I would love to have get an email and then further discuss this exciting research.
Okay, so thanks so much, Dr. Che. Hopefully, when you have a chance to visit Korea, please stop by our lab as well.
Definitely.
Yeah.
It'll be honored to
Yeah.
visit you guys and actually meet in person.
Yes. Thanks so much. So yeah, please thank the Dr. Che, everyone.
Thank you.
Okay. Yeah. 네, 박사님 너무 고생 많으셨고요.